Section 5.5, Zeros of a Polynomial Functions. A new bakery offers decorated sheet cakes for children's birthday parties and other special occasions. The bakery wants the volume of a small cake to be 351 cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width of the cake, and the height of the cake to be 1/3 of the width. What should the dimensions of the cake pan be? This problem can be solved by writing a cubic function and solving a cubic equation for the volume of the cake. In this section, we will discuss a variety of tools for writing polynomial functions and solving polynomial equations. Evaluating a polynomial using the remainder theorem. In the last section, we learned how to divide polynomials. We can now use the polynomial division to evaluate polynomials using the remainder theorem. If the polynomial is divided by x minus k, the remainder may be found quickly by evaluating the polynomial function at k, and that is f of k, where k is the input. Let's walk through the proof of the theorem. Recall that the division algorithm states that, given a polynomial dividend f of x and a non-zero polynomial divisor d of x, where the degree of the divisor d of x is less than or equal to the degree of the dividend f of x, there exist unique polynomials, q of x, which is the quotient, and r of x, which is the remainder, such that f of x is equal to d of x times q of x plus r of x. Now, if the divisor d of x is x minus k, this then takes the form f of x, replacing d of x to be x minus k times q of x plus r. Since the divisor x minus k is linear, the remainder will be constant, which is r. And if we evaluate this for x is equal to k, then we would have the following. F of k is going to equal k minus k, which is 0, times the quotient, plus r, which are left with the remainder r. So in other words, f of k is the remainder obtained by dividing f of x by x minus k. The remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is the value f of k. So let's take a look at a few examples on how we would find the remainder. So in this example, it says find the remainder when we have 4x cubed minus 5x plus 1 is divided by x minus 2. So we're gonna take a look at and use synthetic division to determine how to find the remainder. So we know that the value of k is going to be 2. And then we're going to use synthetic division. So using the leading coefficients, we're going to have 4 for x cubed. Now keep in mind we have a missing term for x squared, so we're going to have 0, and then -5, and then +1. Now again, the first thing we want to do is bring down the 4. So 2 times 4 is going to give us 8, and 0 plus 8 is going to give us 8. 2 times 8 gives us 16. 16 minus 5 gives us 11. 2 times 11 is 22, and 22 plus 1 is going to give us 23. So here we're going to see that the remainder is 23. Okay, now another way for us to be able to check is by finding f of 2, where k is 2. And that's what we're using this definition up here. So what we're going to do is we're going to plug 2 into the function. So it's going to be 4 times 2 cubed minus 5 times 2 plus 1. Well, this is 4 times 2 cubed, which is 8, minus 5 times 2 plus 1. So 4 times 8 is 32, minus 5 times 2, which is 10, plus 1. And this becomes 22 plus 1, which gives us 23. Okay, so we can see here that the remainder, again, is another example. Okay, so here we have x plus 3 as we want to find out the remainder when we're dividing that by x plus 3. Now keep in mind that this is the same thing as x minus -3 from our previous section. So k is going to equal -3. Then we're going to write the coefficients of our polynomial. So we have 4, the missing one is 0, -5, and then 1. So again, we're going to bring down the value of 4, and -3 times 4 is going to give us -12. 0 plus -12 is -12. And we have -3 times -12, which is a positive 36. And 36 plus -5, or -5, is positive 31. And -3 times 31 is -93. And if we add those together, we're going to get -92. So we can see here that our remainder is -92. Now again, since the value of k is -3, we can plug that into our function. So it's going to be 4 times -3 cubed minus 5 times -3 plus 1. So this becomes 4 times -3 cubed is -27 minus 5 times -3 plus 1. And 4 times -27. So if we take 4 multiplied by, let's see here, we're going to get -108. So -108 plus 15 plus 1. Well, let's go ahead and follow the order operations. We have -108 plus 15 plus 1 gives us -92, which should work out here as well. Okay? And then if we continued on here, it says find the remainder when it is divided by 2x minus 1. Now, the reason why I'm providing this example is because technically, okay, this is the same thing as solving for x. So if we take 2x minus 1 and set it equal to 0, then that means 2x is going to equal positive 1, and therefore x is going to equal 1/2. So now the value of k in our synthetic division is going to be 1/2. And then again, we're going to use our coefficients. So we have 4, the missing term is 0, -5, and then 1. So we're going to bring down the 4, and we're going to say 1/2 times 4, or what is 1/2 of 4? Well, 1/2 of 4 is 2. And then 0 plus 2 is going to give us 2. Now, what's 1/2 of 2? Or 1/2 times 2 is going to give us 1. Okay? And then -5 plus 1 is going to give us -4. And then what's 1/2 of -4? Well, that's going to give us -2. And therefore, 1 plus -2 is going to give us -1 as the remainder. And again, if we plug in f of 1/2, where k is 1/2, and we plug it into the function, so this is 4 times 1/2 cubed minus 5 times 1/2 plus 1. Well, 1/2 cubed is the same thing as 1/8 minus 5 times 1/2 plus 1. Now 4 goes into 8 2 times, so that leaves us with 1/2 minus 5 times 1/2 is 5/2. And then if we want a common denominator, 1 is the same thing as 2/2. So now what we can do is then combine like terms. So we have 1/2 minus 5/2, which is -4/2 plus 2/2, which is equal to -2/2, which is equal to -1. So we can see what the remainder theorem tells us. So we can either use synthetic division to find the remainder, or we can use it as an input into the function to determine what the remainder is.